Hello folks, before we get into finishing section 12.3, I thought it'd be a good idea to just recap what we've talked about so far, because last week was spaced out and kind of strange, and I just want to make sure that we're all on the same page before we move on here. So let's go ahead and recap the first couple sections that we talked about. Section 12.1 was all about arithmetic sequences and series. Arithmetic sequences and series. And basically, we ended up with stuff like this. So let me give you an example. If I give you the sequence, -7, -5, -3, and I tell you this goes on, this is considered a sequence. It's just a list of numbers. It's considered arithmetic because in order to get from one term to the other, I'm either adding or subtracting a number. So to get from each number, I'm adding 2. Okay, when that happens, we have what's called a common difference. We use a lowercase d for common difference of 2. Okay, so again, this is either adding, or obviously you could also subtract, hence the word difference, numbers to get from one term to the next in the sequence. Okay, so using the same sequence, I'm going to ask you a couple of questions. First is, I want you to find the 80th term of the sequence. Now, of course, you could sit here and just keep adding 2 and 2 and 2 and 2 and 2 and 2 and 2 until you get to number 80, or you can use the nth term formula, nth term, for arithmetic sequences, which would be, let's see, a sub n is equal to a sub 1 plus n minus 1 times d. So this was one of the big equations from that day, was how to find the nth term. So again, if n in this case is 80, again, we already established d was 2. So if I substituted my values, that would be a sub 80 equals a sub 1 stands for your first term. Our first term in this sequence was -7, plus n is the number of terms, or in this case, the one we're looking for, which is 80. So that'll be 80 minus 1 times d. Again, we already established that the common difference was 2. So then if you just go ahead and do -7 plus 79 times 2, you would get that the 80th term is 151. So that's how to find an nth term of an arithmetic sequence. I could also ask you to find the sum of the first 34 terms of the series. And here I used a new word. All a series is, guys, is your sequence added up all together. Okay, so if I ask you for the sum of the first 34 terms, again, you can find the first 34 terms, add them up all together, or you could use this formula, S sub n is equal to n over 2 times a sub 1 plus a sub n. And again, this is for arithmetic. So in this case, if I substituted my values, again, first 34 terms, that implies that n will equal 34. So when I do S sub 34 is equal to n over 2 is 34 over 2 times a sub 1. Again, I'm still using this original sequence here. So a sub 1 is -7 plus a sub n. That would be a sub 34. I don't know what the 34th term is. So when you use the sum formula, sometimes you may have to go off to the side and also use the nth term formula. If I want to find a sub 34, I'm going to do a sub 1. Again, I'm following this formula up here. A sub 1, the first term is -7, plus n, in this case, is 34, minus 1 times the common difference is 2. So 34 minus 1 is 33, times 2 is 66, minus 7 will be 59. So a sub 34, the 34th term, is 59. Then I can use that number, plug that back into the sum formula, and reduce this. So 34 divided by 2 times negative 7 plus 54. I'm sorry, this should be 59, not 54. And you should end up with the sum of the first 34 terms would be 884. Okay, so that's how to find the nth term and how to find the sum of a series of X amount of numbers. Another type of problem that I could ask you to do is something like this. Write the arithmetic sequence. Write the arithmetic sequence that has 3 arithmetic means. 3 arithmetic means between 3.2 and 4.4. So all an arithmetic mean are numbers that are between two non-consecutive numbers. So if 3.2 and 4.4 start off, or get the bookends of the sequence, 3.2, then I'm looking for 3 terms between them to complete the sequence. Okay, and of course you can kind of logic your way through this, and then when the numbers are easy, there's nothing wrong with that. When the numbers are a little bit more challenging, then you probably want to go ahead and use a formula. Well, if we use the nth term formula, a sub n equals a sub 1, a sub n equals a sub 1 plus n minus 1 times d, then we can solve. The only thing, we have our first term, we have a sub 1, and we have a sub n. In this case, a sub n is there are 5 total, which also implies that n equals 5. Okay, so if n equals 5, then I can substitute a sub 5, which is 4.4, equals a sub 1 is the first term, 3.2. Plus, we said there are 5 terms, so this will be 5 minus 1 times d. So then I can go ahead and subtract 3.2 from both sides. End up with 1.2 equals 5 minus 1 is 4d. And then if you divide both sides by 4, you end up with a common difference of 0.3. So once you have a common difference of 0.3, then you can go ahead and add that 0.3 to each of your terms. It would be 3.5, add another 0.3 to get 3.8, add another 0.3 to get 4.1, and then you can double check. You should end up with your last term by adding another 0.3. So that would be 5 terms in that arithmetic sequence. It's got 3 arithmetic means between your bookend numbers, 3.2, 4.4. So that's dealing with arithmetic sequences. Then in 12.2, we dealt with geometric sequences. And guys, I would say that the easiest way to compare the two, 12.2, geometric sequences in series. Geometric sequences in series is this. Arithmetic sequences in series are where you add or subtract a common difference to get to your next number. Okay, so that's basic arithmetic, mathematical arithmetic, arithmetic sequence in series. A geometric sequence in series is going to be, so let me give you an example, number 3. The square root of 3, negative 3, 3 square roots of 3. I'm going to say, okay, this is my sequence. And for a geometric sequence, in order to get from one term to the next, we are going to multiply, or you can think about dividing if you'd like, which is called, instead of a common difference, it's called a common ratio, and we use the variable r. So you have to figure out what is being multiplied to get from one term to the next. Anytime you jump from positive to negative, or vice versa, your common ratio will definitely have to have a negative number, because that's what makes it go from positive to negative. Then that negative times another negative gets back to a positive. So it's got to be negative. The other thing is, when I compare these two numbers, I don't have my radical anymore. And the only way that I know how to undo a radical is to multiply it times itself. right? So if I have the square root of 3 times negative square roots of 3, then that gets me negative 3. And then if I have negative 3 times negative square roots of 3, the negative times the negative cancel to give me a positive 3, and then I have to leave the square root of 3 outside like this. Okay, so my common ratio for this example is going to be negative square roots of 3. So we'll do a couple of the similar questions that we did for the arithmetic sequence for this geometric sequence. The first part A is going to be to find the 7th term of the sequence. Find the 7th term of the sequence. Now, for a geometric sequence, these have different formulas because they involve r instead of d. So the nth term formula is a sub n equals a sub 1 times r to the n minus 1 power. So that's how you find the nth term of a geometric sequence. If we use this to find the 7th term, that would be a sub 7 equals a sub 1 is your first term. Our first term is the square root of 3 times r to the n minus 1. We already established that the ratio was negative square root of 3 to the n minus 1. Again, n is 7, so that'll be to the 7 minus 1 power. Now, it's crucial that you put this negative square root of 3 in parentheses because all of that is being raised to the n minus 1, right? All of r is being raised to the n minus 1. So what happens is when you simplify that, they get the square root of 3 times negative square roots of 3 to the 6th power. And you have to actually calculate what that is. Well, if you have a difficult time doing that quickly, mentally, write it out. This would be the square root of 3 times negative square roots of 3 times negative square roots of 3, 6 times, right? And then the benefit of doing that is that we can kind of not cancel them out by pairs, but actually multiply them in pairs. If I just multiply negative square root of 3 times negative square root of 3, and negative times a negative is a positive, and then square root of 3 times square root of 3 is just 3. Same thing here. Negative square root of 3 times negative square root of 3 is just going to be a positive 3. And then negative square root of 3 times negative square root of 3 is also going to be a positive 3. And then the rules for radicals is that you can multiply stuff not in a radical together, but you have to leave the one that's inside the radical alone. So the square root, 3 times 3 is 9 times 3 is 27. So the 7th term will be 27 square roots of 3. I could also ask you to find the sum of the first 6 terms of the series. Again, there's the other word, right? The sequence is just the list of numbers. The series is when we start to add some things together. The sum for a geometric series would be s sub n equals a sub 1 times 1 minus r to the n power all over 1 minus r. So if I substitute in what I know that my first term, a sub 1, is the square root of 3. So if I want to find s sub 6, it will equal the square root of 3 times 1 minus r to the n power. Again, we already established that r is negative square root of 3. To the n power, it's going to be to the 6th power. And then all of that is over 1 minus negative square root of 3. So then we'll just simplify what we can. So let's see, it would be the square root of 3 times 1 minus negative square root of 3 to the 6th power. The reason I actually chose this number was because you already figured that out. In the last problem, you did negative square root of 3 to the 6th power when we wrote everything out. It's essentially just 3 times 3 times 3, which was 27. So that'll be 1 minus 27 all over 1 minus negative square root of 3 will change to plus square root of 3. And then if I simplify this a little bit further, 1 minus 27 is negative 26 square roots of 3 all over 1 plus the square root of 3. Now, technically, this is not considered simplified in many circumstances because we're not allowed to have radicals in the denominator. We would have to multiply by the conjugate, which would be 1 minus the square root of 3 over 1 minus the square root of 3 and go for there, but that's just a little bit lengthy at this point. I'm just mainly reviewing how to find sums using the formula. And in fact, in some calc classes, professors are okay with radicals in the denominator. So that's just going to be something as you go to next year, whether it's calculus or college algebra, just get your professor's thoughts on radicals in the denominator and whether or not they will accept answers like that. So I'm okay with you leaving this here in this circumstance. Okay, then the last thing we discussed was starting to talk about 12.3, which was on infinite series. Infinite series. And basically we had two big takeaways, which was about limits. So it was basically if we listed some numbers, what value were they all getting really close to, which was kind of like asymptotes, right? So we said that we knew that the limit of 1 over n as n approaches infinity. So as n gets bigger and bigger and bigger, we start with 1 over 1, 1/2, 1/3, 1/4, 1/5, 1/6. As n gets bigger, we're dividing 1 by a really, really, really big number. The limit of this would be 0. The limit of 1 over n would be 0. And we also discussed, if I asked you the limit as n approaches infinity of just a constant sequence, right? 5, 5, 5, 5, 5, then that will approach 5. In other words, it will approach the constant. So these were the other two big takeaways. And the other one was that the limit of 1 over n to any power is also 0, whether that's 1 n squared, 1 over n cubed, 1 over n to the 5th, and that applied no matter what. It approached 0. So then we did a few examples, such as number 4. If I asked for you, what is the limit as n approaches infinity? My n's kind of look like h's sometimes. Here we go. The limit as n approaches infinity of 4n squared minus 5n all over 3n squared plus 4. So again, we know the limits of 1 over n to some power and the limits of constants. We don't know the limits of these things individually. So one of the tactics that we used was to divide every term by the highest power. In this case, it's n squared. So this is the same thing as the limit as n approaches infinity of, take all your terms, 4n squared divided by n squared, minus 5n over n squared, all over 3n squared over n squared, plus 4 over n squared. And then reason for doing that was because then we can actually simplify this to smaller numbers. So then we could say, okay, well, this is the limit as n approaches infinity. 4n squared over n squared reduces to just 4, minus 5n over n squared reduces to 5 over n. Now, again, I recommend you writing this to kind of save yourself a step. Write this as 5 times 1 over n, because that's the constant, and that's the 1 over n value that we need, because we know the limits of those. All divided by 3n squared over n squared is just 3, plus, again, 4 over n squared, we should write as 4 times 1 over n squared. And then when you actually take the limit, you no longer need to write the limit as n approaches infinity. So if I don't write that anymore, the limit as n approaches infinity of 4 is 4. Minus the limit of 5 is 5. The limit of 1 over n as n approaches infinity is 0. All over the limit of 3 is 3. Plus the limit of 4 is 4. Times the limit of 1 over n squared is also 0. So then, of course, these terms multiplied by 0 essentially disappear. leaving us just with 4 over 3, which we talked about that as well, that these are actually just using basic horizontal asymptote rules. If you have two variables with the same degree, that you just divide their coefficients, and that gives you a horizontal asymptote. In this case, that's also considered the limit. They're not all going to be that easy and straightforward, but you can use that to help you check your answer. But I need to see the limits being used here throughout. Okay, so that was infinite series, and that's how to find the limit. But then we also talked about some scenarios where the limit did not exist, such as the limit as n approaches infinity of -2 to the n power. Now, I gave it away telling you that it doesn't exist already, but I want to remind you why. If I actually write out a list of numbers, so let's just do 4. A sub 1, A sub 2, A sub 3, and A sub 4. So I'm going to plug in 1, 2, and 3, and 4 for n. -2 to the first power, anything to the first power is itself. So it's just -2. Then I plug in 2. -2 squared is -2, because it's in parentheses, times -2, which is +4. And then -2 cubed is -2 times -2 times -2, which is -8. And then -2 to the fourth power is -2 times -2 times -2 times -2, which is a +16. And as this sequence continues, what happens is that I'm going to bounce back and forth between a negative number and a positive number. Well, there's no way that I can predict what number this sequence is going to approach if I don't know when it's going to land on positive and when it's going to land on negative. This will never actually approach one particular number because it's going to keep jumping back and forth from positive to negative. So in that case, do you put D and E when the limit does not exist? Number 6, what about the limit as n approaches infinity of 5n? So again, I want 5 terms. A sub 1, A sub 2, A sub 3. No, let's just do 4. So if I plug in 1, 5 times 1 is 5. If I plug in 2, 5 times 2 is 10. 5 times 3 is 15. 5 times 4 is 20. And what's going to happen is I can't really pick a number that this is going to meet one day or get really, really, really close to one day, because it's just going to keep growing. We use the phrase arbitrarily large in the definition from last week. When that happens, this does not exist. Now, technically, the number does not exist. However, you might get to calculus, or it'd probably be calculus, where an acceptable answer might be that the limit approaches infinity as n approaches infinity. Now, infinity technically is not a number, which is why we say the limit does not exist, because infinity itself is not a number. Okay, so technically that's why the limit does not exist. However, you may see that later as just approaching infinity. Okay, and that's pretty much what we've got through so far was with infinite series. And so today we're just going to round out 12.3 by talking about infinite, well, that was infinite sequences. Now we're going to talk about infinite series, which, as we discussed, is where you take your sequence and you start adding your terms. Okay, so the thing about an infinite series, it's just the sum of our infinite sequences. Now, here's the deal. You cannot add things that go on forever and ever and ever, amen, in some cases. And basically, there are two scenarios. If an infinite series has a sum or a limit, the series is convergent. The series is convergent. And in this case, what happens is the absolute value of the ratio is less than 1. Convergent. Those were the scenarios that we had up here, where these ratios, if we actually found them to get from one number to the next, would be less than 1. And what's happening is they're getting smaller and smaller and smaller, so we can actually add them up together. if an infinite series is not convergent, in other words, it doesn't converge to a particular number, it doesn't approach a particular number, then it is divergent. And in those cases, the absolute value of the ratio R is greater than 1, and its limit does not exist. So I can't ask you to add a sequence that just continues getting bigger and bigger and bigger and bigger and bigger, because then your sum is also just going to approach infinity. But things like pi, that's the reason that we can actually approximate the value of pi and the value of e, is because their ratios are in such a way that we can add together their terms because they're not growing to infinity. They are converging. They have a limit. So let's do a few examples of what this looks like. Now, there's a formula for this as well. For the sum of infinite in... Nope, that's not how you spell infinite. Infinite geometric series. So for the sum of an infinite geometric series, we're going to use the formula S equals A sub 1 over 1 minus R when R, the absolute value of R, is less than 1. And notice this is not like S sub n. It's not summing the first 10 terms. It's summing the entire doggone series, which is crazy because it's infinite. So how can we add together all those infinite things? Well, here's how. I'm going to renumber it just because this is talking about this portion. Let's talk about number 1. Find the sum of the infinite series by 21 minus 3 plus 3/7 minus ... and just keeps going on and on. Okay, so the first thing we need to do is figure out if we can find the sum, which is going to be based on R. So we know A sub 1 is the first term. The only other thing you have to find is R, which is your common ratio. In order to find the common ratio, you divide one term divided by the term in front of it. So I'm going to start with -3 divided by 21, which is -1/7. So since the absolute value of -1/7 is less than 1, then we can use this formula to say that the sum will equal A sub 1 is 21 over 1 minus R. So it's going to be 1 minus -1/7, which will be 21 over 1 minus -1/7 will be 1 plus 1/7, which will be 21 over 8/7, which you could divide and then I guess convert into a fraction. And I meant to talk about this too if I haven't already said it in class. Rule of thumb is whatever your series or sequence is given in, that's what your answer needs to be in as well. So since they showed fraction in the series, you need to make sure that your answer is also as a fraction or as a simplified fraction. In this case, you would end up with 147/8 as the sum of this infinite sequence. And let's think about what that is. If you actually, if you actually divide, no, the next one's actually going to do better. Hold on. Let's look at our next example. We do this often or we've actually learned how to do it without even realizing it. And if we're given something like, write 0.762 as a fraction. Now, I don't know if y'all remember learning this. You don't have to write this, but just to kind of trigger your thoughts. If you have 0.3 repeating like this, we know that it is 1/3, but we also may have been taught that if something repeats like that, then instead of counting this as like the tens place, you almost count it as like the nines place, if that makes sense, to where this would be like 3 over 9, which would reduce to 1/3. So that's the kind of stuff that we're actually going to be using with these geometric sequences and series. And here's how it works. If I write this decimal as a sum of fractions, that would look like this. 0.762 repeating would be the same thing as, if I wrote this number as it is as a fraction, that would be 762 over, you have to be cautious with your places here, tens, hundreds, thousands. So that would be 762 over 1,000 plus 762 over the next 3 places. So after thousandths, if I do 3 more places, then that would be over millionths, right? Because technically this is 0.762, 762, 762. So the first 3 are represented by 762 over 1,000. This next group is 762 over a million, plus, I could do another one, 762 over adding another 3 zeros, be 1 billion. And then it continues on. That's how I would write it as a sum of fractions. Now, if I use the formula, which says you take your first term, divide it by 1 minus the common ratio, then you get the sum of all of these fractions. So let's do that. In order to find r, you just divide, let's do the second term by the first term. So if I divide 762 over 1 million, divided by the first term, which is 762 over 1,000. Now, dividing fractions is the same thing as keep, change, flip, right? Or multiplying by the reciprocal. So instead of dividing by 762 over 1,000, I'm going to write that as multiplying by 1,000 over 762. And then when we multiply fractions, we multiply straight across, right? But the other thing is, so let me rewrite this without muddying it up. Times 1,000 over 762. The other thing is this essentially turns into one giant fraction. So then 762 over 762 cancels, and then 1,000 over 1 million reduces to 1 over 1,000. So the common ratio is 1 over 1,000. Then if I use that ratio to plug that into the formula which is S equals A sub 1 over 1 minus R, then that would be A sub 1 is the first term, which is 762 over 1,000, minus 1 minus R. So that'd be 1 minus 1 over 1,000. And then your job's just to simplify this. So that'd be 762 over 1,000 over 1 minus 1 over 1,000 is 999 over 1,000. And then again, stacked fractions like this, if you think about it as multiplying by the reciprocal of that fraction, that would be 1,000 over 999. And then you multiply these guys straight across, well, 1,000 over 1,000 cancels, and then you're left with 762 over 999, which is kind of that little trick that I was talking about earlier, where someone just kind of taught us when we were in elementary school that if something repeats with a bar like this, you just pretend that those are over 9s instead of 0s or 10s, right? And then, of course, 762 divided by 999 will reduce to 254 over 333. And if you actually type that in your calculator, 254 divided by 333, you're going to end up with the repeating decimal, 0.762. Don't believe me? Try it out. It's kind of neat. We're going to do one more like this. Number 3 of this type. Write 0.15 as a fraction. Now again, using the trick that somebody probably taught you when you were younger, say, oh, that would just be 15 over 99. And that is true, but I want you to prove that essentially using your infinite series. So we're going to write, oh, and this should actually have a bar on top, 0.15 repeating. So if I write 0.15 repeating as a fraction, as a sum of fractions, that would be 15 over 100 plus 15 over the next 2 places are going to add 2 more zeros, so 10,000 plus, and you actually don't need any more than that. You really only need 2. Because then when we find r, a common ratio is going to be the second term, 15 over 10,000, divided by the first term, 15 over 100. And then we're going to multiply, instead of dividing by 15 over 100, we'll multiply by the reciprocal, which is 100 over 15. And then when you multiply these guys straight across, 15 over 15 cancels, leaving us with 100 over 10,000, which is just 1 over 100. So r is 1 over 100. And then if we use that to plug it into the formula, S equals A sub 1 over 1 minus R. Again, this is only for when the absolute value of R is less than 1, which is true, 1/100. So for us, that'll be S equals, the first term was 15 over 100, all over 1 minus R, which is 1 over 100. So then this is equal to 15 over 100 all over 99 over 100. And then instead of dividing by 99 over 100, we're going to multiply by the reciprocal, 100 over 99. Multiply straight across, 100 over 100 cancels. You're left with 15 over 99, which we said we should have earlier, right? It's using the shortcut. But that also further reduces to 5/33.